Welcome to today's ConSteel webinar. Today's topic is design of taper frame according to the EuroCode 3. My name is András Herboi and I'm going to have the presentation today. Just for some practical information, control panel can be hid with the red arrow button, and questions or messages can be sent with the chat option. At the end of the webinar, I will answer them. Few words about the Atom ConSteel webinar series. The first webinar is the today webinar, design of taper frame according to the EuroCode 3. The next webinar topic is the application of the structural imperfection in the design to EuroCode. It will be on 6th of November at 2 o'clock in the European Center time. The last webinar topic is BIM in structural steel design. It will be held on 27th of November. Today's webinar content will be the following. At first I will show you the modeling of a taper frame with a 2D meteorological loads generation. Then I will show you the class 4 cross-section design in ConSteel. At the end, I will demonstrate the stability design of the tapered frame with EuroCode General method. Short introduction to the tapered frames and the class 4 cross-sections. What are the features of a tapered frame? Structure, configuration following the moment distribution. Because of this, the structure is more economical, but the cross-sections are templated, class 3 and class 4 cross-sections according to the EuroCode. What are the dominant failure modes of the frames? Cross-section resistance, local buckling of the plates, global stability resistance of the members, back buckling resistance, interaction of global and local stability, and finally the connection resistance. About some words class 4 cross-sections. What is the definition of the class 4 cross-sections? The class 4 cross-sections are those in which local buckling will occur before the attainment of the yield stress is one or more parts of the cross-sections. And how to check class 4 cross-sections? Calculation of the cross-section resistance according to the elastic design, as the case of class 3 cross-sections, but effective cross-section properties have to be used in the standard check. What does it mean, effective cross-sections? How can we determine the effective cross-sections? First of all, the plate slenderness has to be determined. It depends on the following parameters: the appropriate width of the plate. For example, in case of the weft plate of the I section, the appropriate width is the distance between the two rolling radius. The next parameter is the thickness of the plate and the buckling factor, what is depend on the stress ratio and the boundary condition. It is an internal or it is a outside compression element. The buckling factor is given in the EuroCode. Then the reduction factor has to be determined, what depends on the plate slenderness factor and the stress ratio in case of internal plate. This factor is the stress ratio factor. Last step is to determine the position of the non-effective zones. Here you can see the non-effective zones in a cross-section. The position of the non-effective zones depends on the boundary conditions. It is an internal or it is an outside plate, and the stress ratio also. And here you can read the definition of the effective cross-section. Local buckling due to normal stress reduces the cross-section resistance, and the certain parts of the cross-section are excluded from the area and the section modulus. This is what I like to say as a brief introduction, and now let's see how can we design a tapered frame in ConSteel. I would like to show the capabilities of ConSteel with a simple 2D frame. The geometrical parameters of the frame are the following. The span of the frame is 24 meters, the height of the frame is 10 meters, and the pitch of the roof is 10 degrees. First of all, I add the cross-section to the frame. The cross-section of the member is a 300 mm height and 300 mm wide welded eye section. The thickness of the flange is 16 mm and the thickness of the web is 6 mm. First I place the original cross-section, after that I modify the member to tapered member with the tapered member function. So I choose the proper section and I select the line to place the section. And with the tapered member function, I modified the members of the frame. The height of the members at the start point is 300 mm. At the end point is 1000 mm. And with a simple click, I can modify the section to tapered member. The next step is the support system. On the bottom, the frame is supported with a pin support. I select the pin support from the list. I place on the bottom of the frame. Because the ConSteel is working in the 3D, we have to think about the perpendicular supports. The bracing system has to be modeled. So I'm supporting the frame in the y direction with a simple y direction support. Okay, so the model is ready. The next step is the loadings. So I have some pre-created load groups and load cases. I will use this load groups and load cases for the calculation. There is a persistent load group which contains the dead load of the structure and the housing, and there is a installation load cases. We have a wind load group which contains two load cases in the plus x direction, one for the maximum pressure and one for the maximum suction, and one load cases in the plus y direction for the wind. And finally we have a snow load group which contains two load cases, one for the total load, snow load, and one for the half snow load. The proper safety factors and the coefficient factors are loaded from the selected EuroCode National Annex. Now it is the EuroCode recommended values. Let's place the loadings on the frame. First I place the housing and the dead line and then the dead load on the frame. So intensity of the loadings is in the Z direction is minus 1.2 kilonewton meter. It's a uniform load, and I place both on the columns and on the beams. The self-weight of the structure is automatically added to the load cases. So next load case is the installation. The intensity of the loadings is minus 3 kilonewton meter per meter in the Z direction, and I'm add just to the beam, to the roof. The next load is the wind load. For the wind loads, I'm using the 2D wind load generation functions of the ConSteel. Here we can find the wind actions on the line load window. In case of wind load, the velocity pressure has to be set. It can be set manually or can be determined by the terrain category. If we click on the 3-dot button, so I now select the second terrain category, and I have to set the basic wind velocity, and it is calculated from the fundamental value of the EuroCode and multiply with the directional factor and the season factor. These factors and values come from the EuroCode recommended values. Okay. Now the internal pressure is neglected. For the external pressure, for the wall, and start with the wall. I have to select the surface type. It's a wall. The wind direction, it's 0 degree. It's the same. It is the +6 direction. And I have to select the wall view. It's a front wall because the wind direction is +6. I have to set the frame distance. In this example, it's 6 mm. And now we can see the zone figure, and we can see the actual CPE values. With the OK button, we can place the loads on the selected member. The next column is the other side of the wall. The surface type is wall again, but the wall view is not front, it's a back wall. This is the E zone, and you can see the actual CPA values again. And now we can place the loads. Okay, the last one is the roof. I select both of the beams. Now I go back to the external pressure window. I change the surface type to dual pitch roof. We have to add or set the position of the frame because of the interaction. And in this case, if we have a dual pitch roof, we have 4 different wind cases. The first one is when this part of the root is sanctioned, and the other part also. The second part when the left side of the roof is sanctioned, and the other part is compressed. The case 3, when the left part of the roof is compressed, the other part is sanctioned. The last one is when the whole roof is compressed. In this load cases I placed when the whole roof is sanctioned. And with the place loads button, I can place the proper wind load to the roof. The next load case is the wind +6. Again, I place the wind loads to the column. It's a wall. It's a front wall. Place again the same load than previous. The back wall. Okay. And from the roof, yes, the surface type is dual pitch roof. And now I select the last case when the whole roof is compressed. Okay, the next wind load is the +y direction. I select again the column. The surface type is wall, but the wind direction is not 0, it's 90. And it's not a back wall, now it's a side wall now. Here you can see the CPA, the actual CPA values. Now I can place the load for the other column. It's a side wall again. The wind direction is 90 degree. And for the roof, I select the surface type dual pitch roof. The wind direction is 90 degree. And in this case, we have just one wind case. The whole roof is sanctioned. Okay. The next load type is the snow load. For the snow load, I'm used again the 2D snow load generation functions of ConSteel. I select the roof, and the last tab on the line load we can find the snow load, the characteristic snow load, the wind factor and the temperature factor is automatically loaded from the selected ENA, but we can change it manually if you want. For the shape factor, the surface type has to be chosen. It's a dual pitch roof. The frame distance is 6 mm again, and in this case we have 3 different snow case. The first one is the total, the second one is when the left side of the roof is loaded with half of the snow load, and the third case is when the right side of the roof is loaded with the half of the snow load. Now I choose the first one. The snow load is in a global projection system, but it's automatically selected by the ConSteel. And now I'm place the load. The last snow load is the snow half. So in this case, I place, for example, the case 3 when the right side of the roof is loaded with the half of the snow load. Okay. Next step is to create the load combination, what can be created manually, or we can use the automatic load combination generation functions. With these functions we can automatically generate the selected load combinations if we create the proper load groups and the load combinations. Here we can see the created load combinations. The next step is the analysis. I calculate first order, second order, and buckling analysis for the all load combinations. So all of the results can be seen in all of the load combinations. From the first drop-down menu, we can select one of the calculated analysis type. From the second drop-down menu, we can select the load cases, and from the third drop-down menu, we can select the result type. We can see the deformation in the selected load combinations, or we can see the internal forces, for example, the moment distribution. And if we moving on of the diagram, we can see the actual values of the moment in the selected point, and with right click we can place more marker on the diagram or on the contour surface. So we can see the results on the graphical window, or we can see in in table also. You can see all of the values, the extreme values by members, or we can see the user-defined values if we place marker on the structure. It will be the user-defined values table will be contains the results from this marked point. Okay, let's see the buckling result. If you see the result of the buckling analysis, the dominant buckling in all of the load combinations, if you see the results in the load combinations, so the dominant buckling in all of the load combinations is the flexural torsional buckling of the column. If you see, it's torsion and buckle between the support points. In the top view, you can see. Let's go further to the global checks tab. Here you can find all of the standard checks, what can be performed for the whole structure. First, calculate the cross-section checks according to the second order analysis. The ConSteel performed all of the possible examination in all of the load combination for the all load, for the all finite element. What we can see is a summary of the results. The results can be seen in the graphical windows again, and if we moving on the structure, we can see the utilization of the point, or can be seen in table format. In the table result, the dominant load cases, the dominant examinations, and the utilizations can be seen for each finite element point. We can order it by the utilization, or by the load combination, or by the bar member. You can see the highest utilization point is on the top of the column. If you would like to see the detailed result, with the right click, the section module can be opened from the selected final element point. In the section module, all of the performed standard examination can be seen. You can see the summary. This is the same like on the graphical and in the table result. You can see the general elastic resistance. This is the dominant. You can see the utilization, the applied part of the standard, and all of the parameters what were used for this examination. You can see the pull resistance of the sections, the compression, the bending about the major axis. You can see the minor axis shear. And if you see the section class, the cross section is class 4 cross section, and its classification is calculated from the actual stress distribution. And if you see the model of the cross section, the non-effective part of the web was excluded from the section. The conservative interaction resistance also was calculated. You can see the utilization, and because this cross section is a class 4 cross section, the web backlick resistance also was calculated. Now I'm load another section to the section module and show you what are calculated in case of class 4 cross-section in ConSteel. This section is a very high and slender cross-section. First of all, I add some load cases. I add 2 poor cases and 1 interaction load cases. If you see the EuroCode standard checks for the first load cases, we can see that the non-effective zone is excluded symmetrically, and in the effective properties, so here's the non-effective zone, and if you see the calculation, the effective properties are used in all of the examinations. Here you can see the effective properties, and if you see the compression, we also use the effective area of the cross sections. Let's see the calculation in case of second load case. It's a bending. In this case, the non-effective zone in the compressed part of the web. And if you see the examination, it's also a section, class 4 cross section, and we use the effective section modulus. But if you see the classification, just the web is class 4, the flanges are class 3. And if you see the calculation in the last interaction load case, we can see that the non-effective zone is larger than previous because the compression part of the web is bigger because of the normal force and then the bendings. Okay, let's go back to the model and see the stability design. The stability design of tapered frame may be performed by the general method of EuroCode. This is the general method. The method is based on the calculation of the design load amplifier. Here, the ultimate resistance factor, and the critical load amplifier. The design load amplifier is related to the resistance of the critical most loaded cross-section, while the critical load amplifier is related to the elastic global stability of the structure, what was calculated during the analysis, the buckling analysis. If you see the result, the dominant examination is the global stability resistance, and the utilization is a bit higher than 100%. And if you see the detailed result, we can see the parameter of the global stability resistance. you can see what is the dominant examinations now. You can see the alpha ult key, the alpha CROP, the key, and the other parameters. So now the design of the tapered is done. If you would like to see the shear buckling of the beam, we can convert one of the members to plates, or all of them. And go back to the structural members, and I'm converting this beam to plate. The structural member tab, we can find the convert members to plates function, and with this function we can convert the members to plates. Now it's ready. And if you run again the calculation, now I'm calculate just the 12 load combination. This is the dominant. And if you run again the calculation, we can see the shear buckling of the beam. Sorry for the slow calculation, but I'm using a laptop for the demonstration. So it's ready. And if you see the buckling, so if you see the buckling analysis, the first buckling mode in the dominant load cases, the shear buckling is the shear buckling of the plate of the beam, webs of the beam. And if you see the higher eigenshapes, it's all buckling, shear buckling. If you would like to modify the buckling mode, we can add some extra stiffeners or holes to the plate model with the plate function or with the wall function. But if you see in the global check, the web backlink resistance is calculated by the ConSteel, but we can see with surface or with plates how looks the buckling shapes of the beams. Okay, so for now I'm done with my presentation. So if you have some questions, please write in the questions window. So if you haven't got any questions, I would like to thank you for your attention. I hope you enjoyed, and it was this presentation was useful for you. And I would be happy to welcome you back to our next webinar, what will be at the beginning of November. So thank you very much, and goodbye.